So we're sort of moving into a new phase of the class. We sort of just went through, well, the theme was sort of this hardness, this empty completeness. The idea that A, some simple looking problems might be hard, and then B, this amazing conclusion that actually they're equivalently hard. Get a polynomial time for one, then we'll get a polynomial time for all. And that will still be present, uh, forever, right? That there may be variations of various problems we look at. Small tweaks only becomes much harder or something like this. Uh, so while that still is there, that won't go completely away. I think the next couple lectures or so is going to be about some kind of well-behaved combinatorial problems and graphs, basic problems, and we'll be back to kind of doing algorithms that work again for the most part. Uh, with a few curveballs thrown here and there just to keep you on your toes. So today is about a topic called spanning trees. So, okay, this apparently has some real historical origins. So I guess once upon a time, we invented electricity, and we decided, okay, we're going to have to connect all the houses together with electrical wires. Or maybe one of these houses is a power plant or something, I don't know. And so you might have some idea of where you could put electrical wires. So there, all the yellow lines are like edges you can pick. And you want to connect up all the houses to each other with a minimum amount of electrical wire. So for the sake of discussion, let's say the amount of wire is proportional to the length on the screen. So this is a relatively short wire. That's a longer wire. Okay, you want to minimize the amount of copper you use or something. Okay, so maybe I'll let you all look at it. But the goal is to try to identify, some set of wires so that every house is ultimately connected to every other house. This is undirected. The wires are undirected. Doesn't mean they're connected directly. It means, you can have a path. Okay, so I'll give you a chance and then we'll choose some wires together. All right, have we looked at it enough? Maybe, okay. All right, so let's see, what looks like copper? That looks like copper. Okay, so just tell me which wires, I numbered the houses. And so you could tell me which wires you want me to add and we'll see if it looks pretty good. Sorry? 6 to 8. Okay, we'll take that one. All right, we'll take this one. So you guys seem to like the shorter one so far. Okay, that's a good. Okay, this also raises a point. So if you're looking at these two wires, uh, given what we already have, they're sort of play the same role in the sense that this will connect, either of those wires will connect this to these three. In fact, all three of these wires have the same role at this stage. So you probably want to take the smaller one, which let's say is between 6 and 7. Okay, good. So we're gradually forming some basis for decisions. What else? 8 to 9. Okay. Would it make sense to, um, there are problems where maybe you're allowed to pick a house and you get all of the edges next to it for free or something. That's not the problem we're solving. Um, so this particular model takes no consideration, like you don't get a discount if you have a house with many wires or anything like this. Yeah? Someone? 3 to 1. Okay. 6 to 4. Oh, 4 to 9 seems shorter and it gives sort of the same effect, connectivity wise. 4 to 2 and 2 to 5. So now everything is connected, right? Is there any clear way to improve anything? I know the lengths are a little ambiguous. Okay, well, who knows? So, okay, but you get the sense of the problem, right? So, and you build a little intuition. So maybe some observations. Let's see what we have pre-computed. So, okay, well, one is that we stopped sort of as soon as everything was connected. And there's no point in going further. That would just introduce redundancy as far as connectivity goes. So there's no reason to have a cycle. You have a cycle, okay, just get rid of one of the wires. It's not helping you. That, there's one. Another observation. At least intuitively, it seemed like we should try to take the shorter wires. I mean, we often got in cases where we could pick one of three, and then it was very clear. But in general, it seemed like every time, I think our very first choice overall was this wire when we did it as a class. So there seems to be some intuition there. We haven't really been able to justify it. And then, I guess by definition of connectivity, how did we? One way to know we're done is like if I look at any other wire, I could find some other path that sort of already connects the endpoints. Now, one thing to point out is that, for example, was this wire here, which is a pretty long one. The path looks even longer, right? So this isn't like, this is still like a shorter connection between these two, but somehow we're okay with that. So there's a little bit of funniness there. Okay, so, right. Okay, so I think that this is going to be a lecture full of terminology, so bear with me. Um, so suppose I have some undirected graph and a set of edges f. Okay, so a circuit, uh, well, first just in a graph, is any walk that starts and ends at the same vertex. It can even repeat onto itself. Okay, so you're walking around and you start and end in the same place. Okay, and a forest, I think you all know, is any set of edges with no circuits or equivalently no cycles. Okay, so yeah, there's no cycles in these edges. We call that a forest. Of course, we've seen trees and forests before. A tree is a forest with only one connected component. So if I added a few more edges, so there's no islands left and it's just one big continent, then which there's a good word for, but I kind of forget. Then you have a tree. Okay. All right. So those terminologies you already knew, but maybe not so much these. So one word in the title was spanning trees. So this verb span is going to come up a lot. So let's say I have a set of edges S, and it's going to span some other edge E if it already connects the endpoints of E. Okay, so there's E, and the endpoints I can already get from one end to the other in S. That includes edges in S. So this edge here is also spanned by S. It's spanned by itself. Okay. And we say that a set of edges is spanning if it spans every edge in the graph. Okay. Good. So with those terminologies, we're going to study two problems first, I guess, or the whole time. Okay, so one is a maximization problem and one is a minimization problem. So remember the definition of a forest is you can't have cycles. So that sort of puts like an upper limit on how many edges you can take. So one problem is to try to find a forest of maximum cardinality. Take as many edges as you can. Okay? And then once we get through unweighted, we'll do the weighted case. That might happen more on Wednesday. We'll see how it goes. in which case you want to get a maximum weight forest. And now a spanning set, that means you have to already connect every edge in the graph. So that's almost like a minimum requirement, right? So now your goal is to try to take as few edges as possible while spanning every edge in the graph. At some level, the original connecting up the town problem could be thought of as more of a spanning problem. You get the minimum amount of wire to make sure everything is connected. Okay, and then we'll introduce weights and we'll try to get a minimum weight after that. Okay, and one of the themes that's going to come up is that we're going to study these problems together at the same time, and then we're going to see why that's useful. Okay, nothing down here. Okay, so maybe here's the first such example where you can start to see a little like yin and yang about these two problems. So let F be any forest and let S be any spanning set of edges. And suppose G is connected. Okay. The claim is that F has at most n minus 1 edges, and that S has at least n minus 1 edges. Okay, so you can see that they're sort of like on opposite sides of some magical wall here. Okay. So we'll just do each of these separately one at a time. Okay, we can start with the forest side. Any ideas for trying to show that any forest in the graph can have at most n minus 1 vertices, edges? Yeah, so we want to argue at some level if you have more than n, you must have a cycle. So I think maybe this is something that's probably intuitive to many people. Maybe, maybe not. I don't know. But at the very least, it's still a matter of trying to articulate it clearly. Okay, suppose f had n edges. It's awkward at the very least, right? It's not so easy to explain. Yeah. Yeah. Yeah, maybe something like this. How about well, okay. Here's one way to argue it. Um, yeah, there's a couple of different ways to do it. So here's maybe an incremental argument. So I'm going to imagine starting with an empty set of edges. That's a forest because there's no cycles, there's no edges. And we'll keep trying to add one edge at a time. And as we do it, we'll count the number of connected components left in the graph with respect to F. So initially there's no edges, there's n connected components, there's n vertices. And every time, and I think this is very much the intuition, the suggestion, every time I add one edge, it's not creating a cycle. Right? So if I add an edge to a forest and maintain a forest, it's not going to create a cycle by definition of forest. So it must be an edge between two different components. Those components get glued together and the number of connected components decreases. So for any forest, as you build it up from 0 to the final thing, each edge, since it's not inducing a cycle, needs to decrease the number of connected components by 1, and there's a minimum of 1. Okay. Yeah, so it's a matter of do I mean unconnected components? So we think of like one of these as a connected component, and then jointly they form connected components that you're right are disconnected from each other. So it's a little funny terminology, but that's how people typically use. Yeah. Okay. So that would be at least one way to argue maybe something that I'm guessing many people felt was true before. Okay, there's probably other ways to explain it clearly. Okay, how about this one? This one's maybe a little more awkward. So suppose I have a set of edges in a connected graph that spans every edge in the graph. Okay? And how can I try to argue there's at least n minus 1? No, no, no. I can take all of the edges, right? S is just a spanning set of edges. I can take all of the edges. No, it's not a tree. Or not necessarily a tree. Yeah. Yeah, so every node must be incident to at least one edge of my spanning set. But that would actually only guarantee n over 2 edges, because I could be double counting. So, uh, sometimes we call this a matching, but this is two edges over four nodes where every vertex is incident to an edge, right? But it's not a spanning set if it's a connected graph. That would have to look more like this or something, right? So it's not quite that. It's getting closer. Oh, yeah, sorry. Okay, I think, okay, so somehow there's some idea of like, okay, as I kind of add connectivity one node at a time, I'm adding at least one edge or something, and I should get, yeah, so let me do something that I think is structurally very similar to what we did with the forest, but maybe slightly in reverse. Okay, this is just like trying to take the idea and at least my best attempt to make it very clear on paper. So um, I start with some spanning set of edges, and because it's spanning and the graph's connected, that means there's only one connected component, right? And now imagine removing one edge at a time from my spanning set. So each time, if I delete an edge like in the middle, if I delete this edge or something, that doesn't actually decrease the number of connected components. Okay, so maybe it goes down by 0. Or in a more interesting case, it's an edge across, it's sort of the last edge, and it'll actually create more connected components, right? But no matter what, you can only increase the number of connected components by at most 1. Okay, so if I'm counting the number of connected components as I delete one edge at a time, the number of connected components goes up by uh, at most 1. Could be 0, could be at most 1. And I also know that once I delete all the edges, I'll be back to n connected components. So I have to decrease at least n minus 1 times, so at least n minus 1 edges in S. Okay, so I think that's the idea, but this sort of uh, makes it easy to read. Okay, so this is those neither of those proofs were particularly deep. Um, okay. Okay, here's maybe a follow-up. So last time I did, suppose the graph is connected, right? Now suppose you have k connected components, and you have a forest. So the graph itself wasn't connected to begin with. It kind of looks like there's one connected component, another connected component, right? This is maybe k equals 3. Okay, these are Picasso's graphs. And so the claim then is that any forest subset of these edges that forms a forest has at most n minus 3, and any spanning set has at least n minus 3, where n is the total number of vertices all added up. Why? Uh, okay, so we once talked about strongly connected components. That was often in the context of a directed graph. So here, yeah, there's not or strongly connected components aren't so interesting in a sense that there's always two directions. So, the DAG would just be three isolated nodes, I guess, and so. Mhm. Okay, so let's say that this first component had n1 vertices, and n2 and n3. I know that n1 plus n2 plus n3 adds up to n. Of course, that could be generalized to nk. So how many edges can I get from here? Okay, so I can get at most this here, at most this here, at most this here. I add them up, and you'll get n minus 3. Okay, and then the spanning will be the same, but in the opposite direction. So all these less than equal twos will become greater than equal twos. You add them up. So, okay. So this statement is just applying the above one to each component separately, putting them together. Okay, so these are fairly elementary um, observations, just kind of teasing through, oh, what does it mean to have no cycles? What does it mean to be spanning? All right, so, okay, here's where maybe things get more fun. I don't know. My sense of the word fun. Okay, so first some definitions. So I'll say a forest is a maximal forest if I can't add any more edges to it. Okay, that's not saying it's maximum. It's just saying here's a set of edges, and if I try to add any other edge from my graph to it, it creates a cycle. Okay, so maximum means it really has the maximum size over any possible forest. So they sound similar, but they mean different things. Maximal versus maximum. Maximal is sort of a local property. Can't locally change it to make it bigger. Maximum means I've looked at all the forests possible. This is really the maximum cardinality. Okay. And same thing on the spanning side. So minimal, right? We're trying to make things smaller. Minimal means I can't remove another edge without creating one of these problems because some edge is no longer spanned. Okay, some discontinuity. So minimal means I can't remove any more locally. Minimum means it's truly the smallest possible set of edges that's still spanning. Okay, so local versus global. Okay, and one thing kind of interesting is that okay, we would love to get algorithms for maximum forest and minimum spanning tree. But suppose I said, oh, can you give me an algorithm for maximal forest? What might you do? I just want a maximal forest. Yeah, so maximal just means I cannot add another edge. Maximum means it's truly the maximum possible size. So one is sort of a local optimal. That's not obvious. There are many problems where maximal is not equal to maximum. So in general, right, if you're doing you're minimizing, you're trying to find a point that minimizes a curve, right? Like you have a curve like this, right? So this point might be minimal. Because if I look nearby, it's smaller than everything next to it. But if I had drawn it maybe more exaggerated, this would be a minimum. This is truly smaller, smallest, right? This is always something that comes up with all of our machine learning models, is that, gradient descent, if you're not working on a convex function, then you can try to get a local minimum, which is to say it's minimal. Small adjustments won't help. And it's very hard to argue it's minimum in any meaningful way, right? That's why convexity is so important. So if you have something like convexity, or the opposite, concavity, then maximal does mean maximum. But in general, that's not the case. For good reasons, I might not be able to provide an example, but bear with me. We'll get there. Still, if I ask you, just work with me for a moment to come up with our goal is to get a maximum forest, right? And we're going to do it in a way where we justify and prove things. But if I just asked you, oh, can you first compute a maximal forest? What might you do? Yeah. Yeah, a greedy algorithm is just fine. Just keep adding, 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 right? So maximal is algorithmically very friendly, but not necessarily what we're looking for, which is maximum. But there's certainly algorithmic appeal to maximal, right? Same with minimal, right? I can start with all the edges in the graph and keep removing edges. I don't know if I get the minimum, but I will get a minimal set of edges. Okay? So if we want to argue that they're the same, okay, now we have to actually be careful and do some real analysis. Okay? But algorithmically, I do know how to get maximal and minimal. Okay. All right, so here's now what you were maybe hoping for. So here's what we're going to focus on. So suppose I have one forest and one spanning set of edges. Okay. Our claim, or what we're directly going to prove, is that if f is maximal, then it's spanning. Okay. We're also going to show that if s is minimal, then s is a forest. Right? That's what we'll directly prove in a moment. But why is that interesting? What are the consequences for our original problem? Yeah, so why? Or, yeah. So sorry, can you say it again? Yeah. Well, this would prove that greedy will get you a maximal spanning set of edges. Yeah, so why does maximal so let me just help you expand. Why does maximal in spanning imply maximum? Yeah, so why would it? So we actually already showed here that spanning is always an upper bound on any forest, right? So if you get a forest that's also spanning, then you know you have the optimum, because it would be an upper bound on the best you can do, right? Any spanning set has at least as many edges as any forest. So if your forest is spanning, then it's automatically maximum. Okay? And the point I want to make is that somehow, and we'll see more in a moment, it's very helpful to look at this opposite problem. We're going to argue that the greedy algorithm gets you a maximum forest by studying whether or not it's spanning. Okay? And vice versa. I know that being a forest will give me a lower bound on any spanning set, right? From this kind of relatively simple counting argument we did before. So we're going to argue that a greedy algorithm, just removing edges, will get you a minimum spanning set, but by thinking about whether or not it's a forest. Okay, so this is our first example of what are called primal and dual problems. There's actually two sides of the same coin. Minimum spanning set, maximal forest. And this is a paradigm that shows up in many problems. This is just one kind of relatively simple example, okay? And they're going to mutually certify each other to be optimal or optimum, okay? It's often not so easy in a given problem in the wild to know if you have an optimum solution, but in this kind of primal dual setup where you have this opposite and they can mutually certify each other to be best possible, okay, that's very unique, right? That's something to leverage. So that's the real point of this lecture. Okay, good. So, right. And then this, okay, so you have these spanning, we call them spanning forests. Okay. It would be a spanning tree if the graph was connected. Okay, but it's really where these two problems meet. Okay, so let's do this. All right, so the claim is that if F, we'll do one at a time. If F is a maximal forest, then it must be spanning. If F is a maximal forest, it must be spanning. How do we prove this? Yeah. Okay, so here's a forest, I guess. And suppose I'm looking at another edge, right? Now, if my forest was maximal, then adding this should create a cycle, right? That means there must be some path in the forest that apparently I didn't draw, right? So if it's maximal, then there must be some way to connect the endpoints, which means it's spanning. Okay. So if it's maximal, there can't be any unspanned edges because otherwise an unspanned edge you can add to your graph. In fact, we can rewrite, you can also write the algorithm as like, oh, keep adding unspanned edges to F. Okay, so that's very simple, right? Okay, how about the second side? If S is a minimal spanning set, then S is a forest. If S is a minimal spanning set, then S is a forest. Yeah, so let me articulate that a little bit differently, trying to stay true to the definition of spanning and things like this. So suppose I'll load by contradiction. I'll say, okay, suppose not. So S has a cycle. It's not a forest that has some cycle, right? And there's some other stuff going on. If you know that if you delete one of these edges, any path that was going through this edge, like that, could be rerouted around the cycle, I guess like this or something. Okay, so you're not going to lose any connectivity. So every cycle is some kind of redundancy and lets you remove an edge. Okay, if there's no cycles, you have forest. Okay, so good. So at some level, I don't think anything we observed was particularly complicated. We just kind of worked our way through the definitions. But one thing very nice is that it's this perspective, this framing of doing the primal dual, right? We're somehow kind of solving both of these problems at the same time is much easier than if I tried to do maximum forest without ever using the spanning terminology quite like this. Okay, so sometimes this happens a lot in combinatorial optimization. There's some kind of dual problem. You might be interested in a maximum forest, but there's some kind of dual problem, like a minimum spanning set, that if you spend equal amount of time looking at, it's going to give you a lot of hints to solve your original problem. Okay. Um, Good. Great. Okay, so now we can get started on the weighted version. So we just did cardinality. Okay. And now we're going to try to get weight. So I'm going to assume that all the edge weights are positive. Otherwise, for like maximum force, you just would like not take anything. Or no, you just ignore the negative edges anyway and things like this. Okay, so, right. So, but I'm going to assume they're distinct for simplicity. Okay, so if they're not distinct, it'll be very easy to see how to make our algorithms work for this, but there's at least one algorithm for which it's a little bit more convenient in discussion to assume they're distinct, and then you can implement that by just breaking ties consistently. Question? Okay. Okay, so that's our next challenge. But any questions maybe about cardinality before we leap into the weighted frontier? Okay, great. Okay, so our approach is going to center on this notion of good edges. Okay, so good means this. If I have any edge E, okay, or I have an edge E, and I'm going to say it's good if for any set of edges that spans E, so it connects the endpoints, okay, there should be at least one edge on this path. Remember, all the edge weights are distinct, such that the weight of E is at most the maximum edge in here. So one sec, are we doing maximum forest? Okay, forgive me. I think that for maximum force, we might want to flip some of these inequalities. Okay, so I'm going to say that an edge is good if every time I find some other path with the same kind of effective connectivity, connects the same endpoints, okay, I can find another edge where the weight of E is bigger than a weight on the path. Okay, so take any other edge that connects a set of edges that connects the endpoint. Okay, if our goal is to get a maximum weight force, so like heavier edges are good. Okay, our edge should beat out at least one edge on this spanning set. Yeah. That means the biggest weight edge in the entire graph is automatically good. Um, yeah. So you take the biggest edge, okay, and then what? So best would just be biggest weight edge overall. I guess because there's only one, and we're going to want to take many edges. Oh, so maybe this is sort of like doing some stuff. Well, we'll see. Maybe you can reflect and see if this was useless after all. But at the very least, the next slides are set up like this. So okay, but this is just some property of edges, and obviously I'm saying it's good, so maybe we'll try to take them. Okay, but saying at some level I'm interested in connectivity, right? And yeah, okay, so okay, good. So let me correct some of this again. Oh, okay. Okay, did I do the most confusing possible thing? I think I did. So, okay, let me establish this once and for all because the next slides are set up. So I'm going to assume the graph is connected because we can just treat the different components separately. Okay? And what we learned is that a spanning forest always has n minus 1 edges. Okay? So we're going to focus on not the maximum forest problem. We're going to try to do a minimum weight spanning set of edges, which is going to be a tree. That's what we showed. Okay? So we're going to focus on the minimum weight spanning tree problem, which is why, and that's the most common thing in the textbooks. I think that's why I did it this way. So let me say, okay, I'm okay with this version. So if I'm trying to get the minimum weight spanning tree, which is really minimum weight spanning set of edges, now I want E to be relatively small if it's good. So we're just flipping some things. E is good if whenever I draw another path connecting the endpoints, I can find some edge with bigger weight. Okay, the original. Okay, sorry about that. Okay, good. So here's what motivates the definition of good. Okay, and in general, what we're going to do is we're going to just try to understand what's in a minimum weight spanning tree, and then there's going to be 10 algorithms that we can do, right? Just from understanding the combinatorial object better. So let's fix an edge. So I'm saying these are equivalent. Number 2 is saying that E is good. It's just written out for some reason. Okay, and that's equivalent to saying every minimum weight spanning tree contains E. Okay, so these are edges, if we can prove this to be correct, or we can guarantee that every spanning tree contains this edge. Okay, so that means I can always try to take an edge if I know it's good. Right, that would be very helpful when it comes to algorithm design time. Okay, good? Yeah. Edgeway is distinct, yeah. We'll find out. Yeah. I guess many of you have taken an algorithms class before. Yeah. Okay. Okay. So let's prove this is correct. Yeah, we have time for this. So the claim is that yeah. So suppose it was true that every minimum weight spanning tree contains E. I want to prove that E is good. Yeah. Okay. So you're saying suppose there's a minimum weight by contradiction. So suppose there's a minimum weight spanning tree that doesn't contain E. Okay. Uh, one sec. I think you're. Is that correct? Is that the right direction? I'm just trying. You might be doing direction 2. I think you were okay. We can do direction 2. So let's assume that E is good, and now let's try to show that every minimum weight spanning tree contains E, and then let's assume by contradiction that there's a minimum weight spanning tree that doesn't contain E. Okay. So suppose number 1 is false. So that means we have some. I'll write MWST, minimum weight spanning tree T, without E. So here's your minimum weight spanning tree or something. Just trying to draw a tree. And here is E, which is supposed to be good. Okay. All right. So I want to reach some kind of contradiction, right? So what would that be? Sorry? Now you're cheating. Okay. So here's our contradiction, right? I mean, we've set this up. So I'm assuming that there's a minimum weight spanning tree that doesn't have E, but I know that E is good. So here I'm assuming E is good. Okay. And I want to show that having this minimum weight spanning tree exclude E is some kind of logical contradiction. Yeah, so how do I find the edge F though? Just kind of pry that open a little. Well, what if the maximum weight edge is here? That's not very helpful, right? Yeah, so it's spanning, so there's some path connecting the endpoints. Okay, so we just have to identify our set F. Okay, so the tree itself must contain some set of edges spanning E, okay, along its path. And since E is good, um, one of these edges, F, must have bigger weight because E is good, okay? And if we delete this edge and we add E back in, we'll get the same number of connected components again, okay? And we'll get a tree of smaller weight. If I take out this bigger edge, delete this, and then bridge it back together with E, the overall weight will go down because the weight of E is less than the weight of F. That can't happen if blue was really the minimum. Okay, good. So that's one direction. Let's do the other direction now. Suppose every minimum weight spanning tree contains E. I want to show that E is good. So maybe to get us started, I'll just draw a spanning tree that's supposed to be minimum weight. Let me get a different color. And it contains E. Okay, so there's at least one minimum weight spanning tree that contains E. Yeah, so maybe we could suppose by contradiction that E is not good. Okay, suppose E is not good. Then I should be able to, then there must be some edge set, maybe overlaps with this tree sometimes, right? There must be some path out there, also connecting the endpoints of E, where the weight of every edge on this path is less than the weight of E, right? Okay, now what? Which edge? Well, if I deleted E and I added this edge or something, it wouldn't be useful, right? It is true we're going to replace a edge, but how do I guarantee an edge? Yeah, so if I remove this, so just to like pinpoint it more precisely, all I know about this path is it starts in one component and ends in another, right? So some edge, there's at least one edge here. It looks like there's many edges or something. Well, this doesn't quite make sense in the picture, but there must be some edge that goes in one component and goes to the other. It has to be at least one, right? You just like, yeah. So, and that edge you're guaranteed has a smaller weight because all the edges on the path have smaller weight. Okay, and then that's it. Okay, so that's the two directions. And good, good. So let me tee up what we're going to do next time. Okay, so we have this characterization of good edges. We've shown that every minimum weight spanning tree contains any good edge. So we're going to try to analyze this generic algorithm and then we'll try to make it fast. But a generic algorithm is just Start with an empty set of edges, add a good edge, repeat, add a good edge, repeat, add a good edge, repeat. Now there's two questions we'll need to address. One is, will there always be a good edge? And the second is, how can I identify a good edge? But otherwise, all the algorithm we'll look at will be in this framework, and so it'll automatically be correct if this algorithm terminates. If you can fill up a tree with good edges, then what we've shown already shows you're correct. Okay? All right, so that's what we'll do Wednesday. Thank you. All right, then let me review what we did last time, as hopefully a couple more people trickle in. So we're discussing this problem of computing minimum weight spanning trees. A simple application might be like, oh, you want to connect the whole town up with the minimum total length of wire or something like this. And yeah, so there's some terminology we're using very carefully, like a circuit, a forest, a tree. Spanning was a big word. So a set of edges spans some other edge E if it already connects the endpoints. And I think the point of last time's class was to look at two kind of opposite problems simultaneously. One is to compute a forest with as many edges as possible. The other is to compute a spanning set with as few edges as possible. And our proofs, they weren't necessarily complicated. This one was sort of like counting edges as I deleted edges from a forest. In this one, I'm sort of counting components as I delete edges from a spanning set. So not like very complicated arguments. But maybe one thing nice is that we would get this sort of, okay, the number of edges in any forest is at most the number of edges in the spanning tree. N minus k is just almost by coincidence in the middle. All that really matters is f is less than or equal to s. And okay. And so the question sort of got rephrased into this maximal versus maximum question. Maximal just means locally optimal. Maximum means globally optimal. Same with minimal, minimum. We want the global optimum, but algorithmically it's easy to get the local optimum. I can just add edges or remove edges, right? So if I can show that local optimum is equal to global optimum, then we have a very easy algorithm. And so that's what we did. But in particular, we sort of certified their optimality by playing them off of each other, these two problems at once. A maximal forest is spanning, and since any spanning set dominates any forest, that means it's optimum. A minimal spanning set must be a forest, which also makes it an optimum. So it's kind of studying these two opposite problems, where one obviously bounds the other, and then getting them to meet, let them know that you get both of them correctly. Right? This is always like a basic question. How do you even know if you have the right answer? And here we have two opposite problems that certify each other to be correct. So, okay, good. So, that's fine. And then we shifted into gears. There's a little confusion. But we focused on a minimum weight spanning set, which after a discussion we knew would always be a tree if the graph was connected. So sometimes we call this the minimum weight spanning tree. And there, in the last 10 minutes, we had to introduce this idea of good edges. A good edge means that E is good if for any other set of edges that spans E, I could find at least one edge with weight greater than E. Okay. And, okay, that seems a little eccentric, but it becomes more valuable in the following lemma, which we did together. So E is good if and only if every minimum weight spanning tree contains E. Okay, so this is fantastic. And okay, good, good. So that's what we proved. And I left you with this generic algorithm where I'm just going to try to add edges to a forest that starts that starts as an empty forest. Okay, and our algorithm is just going to repeatedly try to add good edges. We've already shown that any good edge will be in any minimum weight spanning tree. So these are always safe decisions. Okay, and we'll return the tree. This is some generic algorithm. And then now the real question is, okay, um, how do you identify good edges? You know, is there even always a good edge, right? And then how fast you can identify and stuff like this. And especially, well, we're going to find out we can't always find good edges. So the algorithms, well, I'll end up showing, I think, 3 different algorithms, but they all have slightly different strategies for finding the next good edge, and that results in slightly different running times and characteristics. But the proof of correctness will just come from the fact that we're always within this framework. Okay, so they're going to actually come at you really fast. So, okay, so here is uh, the main lemma we're going to use to find good edges. Okay, so it says, okay, let H be any set of edges. Here's some edges here, right? So maybe this is H. Maybe it doesn't connect the whole graph. Okay. And suppose, now there's some edges that aren't spanned by H, right? So edges that are sort of within these components, they are already spanned. But these things that aren't spanned, are like edges like in the red. Okay. And of these unspanned edges, identify the minimum weight edge. Let's say it's this one. Okay. The claim is that E must be a good edge. Okay, so if there's any set H for which E becomes sort of the best leftover edge, okay, then E is good. Um, good, good. So how can we prove this? Okay, so to prove E is good, I need to show that for any set of edges F that spans E, the weight of E will be smaller than some edge in the span. So let me give an example then. Let's say that you have some path connecting the endpoints, right? So that'll be some set F that spans our edge E, and I want to argue that that there's some edge in this yellow set with weight greater than E. Yeah, so if I can argue that yellow contains at least one unspanned edge, then we would be okay, right? Because that unspanned edge must have weight greater than E. Okay. And which is to say, if I can argue that H doesn't span F, then there's, all of F, then there's some edge in F. Okay. Okay. So maybe then we just need to argue then that any set of edges F that spans E is not spanned by H. Meaning there's at least one edge in F that's not spanned by H. Yeah. Oh, no. Okay, so maybe one thing we can do is proof by contradiction, right? If purple spanned yellow, so every edge in yellow was connected by purple, right? So I can take every edge in F and replace it with a purple path, right? And it'll connect the endpoints. And I glue all that together, and you'll get one long purple walk connecting the endpoints of E, but then purple would span E. Okay, so there must be at least one yellow edge. Here it's clear that we have yellow edges hopping across components, but as drawn, but there must be at least one yellow edge that's not spanned by purple, right? So maybe that's this one here or something. And so this unspanned edge by choice of E must have weight bigger than E. Okay, and so E is good. It survives any choice of yellow. Okay, so that's all we're going to use. Yeah, okay. So so this we're just going to use this lemma where we're going to just propose some set H and then find some edge that's sort of cut by H, not connected by H. And we'll take the minimum weight one. All right, so what possible algorithms might this suggest? So we can use this lemma to try to make an algorithm because the algorithm just needs to. It gives an easy way to argue that, oh, if I choose this edge, it's safe. It's a good edge. Okay, so what might a greedy algorithm look like? What would be the first edge you take? Yeah, maybe you take the lowest weight one first. Uh, so you just, you take the lowest weight edge or something. What would the second edge be? It would be maybe the second lowest weight edge. Maybe it looks like that or something, right? Now, the lowest weight edge is safe because I could have just taken H to be everything except for that edge, and you would have been okay. Yeah. Or exactly. So okay. So the first edge I could actually take H to be empty. Sorry. The first edge I could take H to be empty. So all the edges are uh, among this set of edges that's not spanned by zero edges, right? So in other words, if I'm labeling sort of in the before the first iteration, I'll take H to be the empty set, and I just find a minimum weight edge. The next iteration, maybe this is the first edge I took, E1, and our sort of certificate, H, could just be E1. So you're just saying, oh, find me the minimum weight edge that's not spanned by the one edge I've taken. After two iterations, you can let your H be these two edges that you've taken. And now this will encode make sure you don't introduce a cycle. Give me the minimum weight edge that's not spanned by the edges I've already taken. And keep going, keep going, keep going. And what's great is that as long as there's at least one unspanned edge, you'll get some minimum weight unspanned edge. You'll always be able to find an edge that you know is okay. Okay. So, all right. So with that lemma or that observation, uh, then you just get this greedy algorithm. But the key point is that each edge you take is okay. The certificate, that set H, will be the tree you have or the forest you have so far. Okay, so that's one greedy algorithm. Any other ideas? Yeah. Huh? Yeah, so when I take an edge E, I want to know that I'm not making a mistake. So I can interpret this lemma as saying if I can find some edge set H for which E the next edge I take is the minimum weight unspanned edge. Uh, then E is safe to take. E is good. We've already argued that every minimum spanning tree contains minimum weight spanning tree contains every good edge. So taking good edges is okay, but I just want to argue that when I'm taking an edge, it is good. So to justify the greedy algorithm using that framework, there's many ways to argue this. I would just use H to be my current tree, in which case the greedy algorithm will keep taking the next minimum weight edge that doesn't introduce a cycle, which is to say the same one, it's not spanned. Okay, so I'm using the solution so far to certify that I'm taking a good solution, a good edge, and then I'm still on the path to correctness. Yeah. Okay. So good. Um, okay. So that's a natural algorithm. The next one's going to be a parallel algorithm. Can anyone think of how to try to construct a parallel algorithm for minimum spanning tree? I know parallel is sort of loosely defined, but at some level, try to come up with a way where you can take sort of many good edges at once. Let me ask another question. Suppose I have a particular vertex. Imagine you're starting completely from fresh, okay? And I'm focusing on one vertex in particular, symbolized by that blue dot. And that has, several edges incident to it, okay? And one of these edges is the minimum weight edge incident to that vertex. I want to argue that for this vertex, the minimum weight edge incident to it must be good. How could I do that? Because if that were true, that's great, because then every vertex can just pick its minimum weight edge, and I'll take a lot of edges at once. But then I would still need to try to argue that, oh, the minimum weight edge incident to a vertex is always good. No. Well, for example, we don't know that there's unique spanning trees or things like this. Well, it's a little tricky because remember, the minimum spanning tree may have several of these edges. I know, but why? We have to articulate this. But there may be several edges that reach blue. Just work with me. Just find a simple set H to prove that this thing is good. It's going to be much simpler. So I'm trying to find some other set of edges H that makes this edge look good. Yeah, let's just take H to be the rest of the graph. Okay, which is very similar to the intuition you guys were trying to articulate. There must be at least one edge going to blue, but this is just going to clarify it. Okay. So H would just be all the edges except for those incident to this vertex. Okay. So the only unspanned edges are the edges incident to this vertex. Now you have your good edge. Okay. So that gives rise to the following parallel algorithm. So I don't know, this is sometimes called Brusca's algorithm. Initially, you start with lots of vertices, n vertices, okay? And so initially you start with n vertices, and every vertex chooses its minimum weight edge. Okay, so this one might choose this one, that one might choose that one. And they might choose the same edge and stuff, right? That may happen. Okay. So here each vertex chose one edge, and some edges were chosen twice because they were the minimum weight edge to both edges, right? So that's one iteration. Now, if I start with n vertices, how many connected components are left? At most, how many? N by 2, because every vertex gets at least one buddy. Okay? So what I can think of is I can just contract this. I can think of collapsing each connected component as a vertex, right? So each of these I'll sort of treat as one vertex, right? And the graph has, n over 2 vertices at most. So we've gotten rid of half of the vertices. And then we just do this again. Okay, this component was the minimum weight edge. This component was the minimum weight edge. Right? So you might contract again. Oops, sorry. Like this. Let me do it differently. Right? So in the second round, you might add these edges. And then you contract those components like this. And eventually gets connected. Okay. So now instead of our certificate H being like all the edges that are incident to the vertex, it'll be all the edges not incident to this whole component, right? Okay. This one actually might be the most practical algorithm. Okay, so that's a very simple algorithm. And then it's not actually the fastest one. You might all know this from being taught it before. So we've done a greedy algorithm, which just sorts the edges in increasing order and keeps trying to add any that doesn't create a cycle. And then we have this parallel algorithm where in the first iteration, each vertex chooses the least weight edge, and then we kind of contract and we repeat. There's at least one more algorithm that's pretty popular. So a third algorithm looks a little bit like the search algorithms we've done. The idea is you start from one particular vertex, any vertex you want, and you'll find the smallest weight edge incident to that vertex. Okay, so now you've had this kind of connected component of two vertices, and everyone else is still by itself. And now you look at these two vertices and treat them almost as one vertex pinched together, or look at the whole component and try to find the next smallest edge leaving the component. So something like this, right? Now you've added three vertices to your component. Now you want to find the next minimum weight edge connected to that component in particular. Maybe it goes like this. Okay. And so you're kind of growing a component out until it gobbles up the whole graph. Okay. So that sort of feels like Dijkstra or BFS or something. Okay, good. So those are three algorithms. They're all immediately correct because they're only taking good edges. Okay. So in fact, we show that you can fill up a tree with n minus one good edges, which actually means that when the weights are distinct, this minimum weight spanning tree is unique because every good edge is in every minimum weight spanning tree. And you found n minus one of them. Okay, so now we just have to like discuss running times. This is relatively easy. Okay, so for the greedy algorithm, the bottleneck is I'm looking at the next minimum weight edge and I need to know if it creates a cycle. Okay, so to that end, what we're going to use is, and we might analyze this later, I'm not sure, but a well-known data structure called the disjoint union data structure. I know it's covered in the data structure algorithm here, but that's at the undergrad level. So you may or may not have seen it, but here are your basic operations. So you start with sort of like n elements and they're in their own set. And basically you can just like take two elements and say, okay, from now on they're in the same set. From now on they're in the same set. And over time you kind of have these subsets that you're forming. So if I take two vertices from two different subsets and say they're in the same set, that glues the whole subsets together. Okay? So you're just gradually forming these things. And your main query is, oh, here are these two elements based on my previous insertions, I mean, my gluing, are they in the same set right now? Okay. So those are the two main operations. So here, every time I add an edge between two vertices, they're going to be in the same connected component. So for us, sets will map to components. So say, okay, these two vertices are in the same connected component. That means that, all the vertices in their prior connected components are now connected. Okay. And then when I want to see if I can add a new edge, I just want to know if the endpoints are in the same connected component. So that's just asking same set. Okay. Now this data structure is spectacularly fast. So if you're doing M unions, which for us is number of edges, because for every edge, I guess it's actually, no, sorry. If you're doing M same set queries and N unions, you're going to do at most N unions probably, because then they'll all be together. Um, the running time is going to be M plus N, something called the inverse Ackermann function of N, which is like a very, 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 very slow growing function of N. I think it's smaller than log log N, it's smaller than log 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 N, it's smaller than log 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 N, it's smaller than log, it's just like a very, very slow growing function. And actually this is sort of a celebrated result insofar as it got this absurd bound. In fact, this is known to be tight. You can't do better than this. Okay, so it's sort of an eccentric math thing. This is almost a constant. Like I think like inverse Ackermann of like number of atoms in the universe should be like 4 or 5 or something. Yeah. Um, so this is anyway. So if we use that data structure, then actually I need to first sort all the edges at first. So that takes m log n time. And then for each edge, we check to see if it's same set. That'll take constant time. And if I add an edge, that'll take inverse Ackermann time. So the bottleneck just comes from sorting the edges at first. So that's easy. Okay, the parallel algorithm. Okay, so first of all, I described the parallel algorithm in phases, where in each phase, all the connected components at the moment chooses their best edge. How many phases will we have? Log n, because each one will have the number of vertices or connected components left. And in each phase, I just need to go through all the components and find the minimum weight edge, right? So one way to do this, imagine first they're just all vertices, right? I can just go through each, so we can maintain for each vertex what's the minimum weight edge I've seen so far. You don't actually have to sort all the edges. You just need to find a minimum for each vertex, right? So I just go through all the edges, A and B, and say, oh, what's the best one I found for A so far? If this is better, I'll replace it. What's the best one I found for B so far? If this is better, I'll replace it. So I can actually just go through all the edges in M time and identify the minimum weight edge for every vertex. Now, for connected components, well, first I need to label all the components, right? So maybe I'll run depth first search from various vertices and say, okay, all these vertices are in component 1, all these vertices are in component 2, component 3, component 4, component 5, right? Just labeling was the first search. And then I can, and you build an array, this vertex is in component 2, so on and so forth. Then you just go through all the edges again. Oh, this is between vertex A, vertex B, vertex A is in component 1. What's the best edge I have for component 1 so far? This vertex B is in component 3. What's the best edge I have in component 3 so far? If A and B are in the same component, okay, I skip it. Okay. So you can do each pass in M time. You don't actually have to sort all the edges. That's the point. Good. So that will be M log n as well. Now, the last one, the search algorithm. This is where we're growing things out. Start at one vertex and we keep adding the next closest, next closest, next closest. What algorithm that we've already studied does that remind you of? So this search version of the minimum spanning tree where I start and I grow a single component. BFS or even, what about with weights? Dijkstra's algorithm also was sort of like always adding the next best edge, next best edge, next best edge. Okay. So this is also very similar. We can use the same Fibonacci heaps from before. So if you remember from Dijkstra's algorithm, we would like insert keys with particular priorities. Okay, so this could be edges with weights. Okay, and so the idea is that, okay, initially I will add all of the edges incident to my first vertex to my priority queue. Okay, and then I'll get the minimum weight edge in the priority queue, right? And that'll give me a new vertex. And then I'll add all of these incident edges to the priority queue. Okay, and keep getting the minimum weight edge, minimum weight edge. Okay. Yeah, so that's it. So if you do that, so the first algorithm is m log n, the second algorithm is m log n, the third algorithm comes up to m plus n log n, just like Dijkstra's algorithm. What's there to say? I think in practice, Borufka's algorithm is probably considered the fastest because, yeah, it's the simplest to implement. Just that's what people say. Also, the parallel aspect is very useful in many. But I guess if you're on a test, you probably want to use the fastest asymptotic running time. Yeah. The Fibonacci heaps sort of seem to incur a big hidden constant. Yeah. Okay. Good. Any questions? Because we're going to transition to the next topic. Okay. The running times to me is not really the point of the lecture. I think the point is A, the primal dual between the spanning and the forest, right? This idea of opposite problems. That's more conceptually interesting. And in general, we sort of had these greedy algorithms for this problems. It's almost the only greedy algorithms we'll see all semester. And in general, you should be very, very wary of greedy algorithms. But when you use it, you want to be really careful, right? We basically had a lot of structural observations and got to understand the combinatorics of the problem really well until by the end, it was like very easy to put together an algorithm. Okay, so this is often, you can use a greedy algorithm, but you want to be really careful and it should really be backed up by a lot of structural understanding. Right? Because at some level, if you can do something as kind of myopic as a greedy algorithm, then there must be something really simple about it, right? And you should be able to articulate it. Okay, because it's not really a very, compared to like dynamic programming, which is effectively doing a brute force search, except it's kind of by a trick being efficient, right? A greedy algorithm is very, very kind of, it's not looking ahead, it's not doing nearly as much, taking as much into consideration as some of these other algorithms. Okay, good. Okay, on to the next thing.